I think we're good. All right, js.la, thanks for coming out tonight. I'm going to be talking tonight about functional programming. I think I have a little bit here for everyone of all experiences. If you're new to JS or if you already know a little bit about functional programming, get a little bit to whet everyone's appetite. But just want to introduce myself real quick. Let's see. Oh yeah, by the way, if you want to follow along, I have all the files and links to the slides on my GitHub. So, and also there's going to be a ton of links in the presenter notes that you'll want to check out later. Anyway, I am Forrest. I got my programming started like anyone in a loss mitigation call center for City Mortgage during the housing crisis. I began writing Excel functions, and functions led to learning SQL, which led to learning about how to model relational data, led to building applications on top of Microsoft Office products with VBA, and I did that for a while. Eventually, I was a consultant and did that for a few years. I dug up my first Stack Overflow post here back from 2013. Turns out you don't have to manipulate the Excel spreadsheet every time you want to do anything. You can calculate everything you want to do up front and then apply that. Anyway, that was where it all began for me. During this, I was going to school part-time at UT Dallas. I am a native Texan. But it turns out that it's really hard to kind of divide your time between full-time work and study. So I decided I need to pick something. So I moved to LA and went to Maker Square. And Maker Square, shortly after that, became Hack Reactor, which more recently became Hack Reactor at Galvanize. Since then, I've been doing full-stack JavaScript. Right now, I work at like David mentioned, a B2B wholesale e-commerce company that is scaling up big time right now. We primarily use React and Node on the back end, but as we scale up, we're looking to move to something a little simpler. And like you mentioned, I'm also a drummer, so I do that every morning and record on the weekends. And in all things, I am supported by the lovely Michelle here, demonstrating her no tears onion chopping technique. Anyway, so we're here to talk about functional programming, but first, let's cover why it matters to me. Turns out, software is hard. And it's hard in a lot of ways that have nothing to do with the inherent complexity of the problems we're actually trying to solve. It's hard because organizations give us this constant pressure to deliver, which means that we end up compromising constantly. We say, oh, we'll come back later and clean it up, but we all know that never happens. And we try to explain to leadership that this is painful. We need to slow down and make things make sense. But it turns out that leadership doesn't really understand the problems we're explaining to them. And to be fair, engineering has trouble articulating these problems to leadership. So in our frenzy to deliver, we don't really plan much. We kind of just dive in. Hey, do this, and it'll work itself out. But as we all know, failing to plan is planning to fail. It's cliche, but true. And without the planning, we don't know how to prioritize the items we're trying to work on. So if nothing is a clear priority, we just kind of pick up things randomly. But these all have nothing to do with code. Then there's the code. This puts our code in a situation where we have all these brittle abstractions. Our beautiful greenfield project grows up into this soul-devouring monster. And then it's brittle because it's ended up in this state where everything is this tangled webs of dependencies, and we have no idea how to decouple everything. It would be nice if we could kind of refactor, but it turns out we can't because we don't have any test coverage. And there's a good reason for that, because our code doesn't exhibit deterministic behavior. So how would we even begin to test it? This leaves us in a sad situation. And in pondering this, I've had a lot of good influences to kind of guide my thinking. One is this talk by Rich Hickey, Are We There Yet? In it, I was introduced to the concept of incidental complexity. It's all these problems that we add to the inherent complexity of the problem we're trying to solve that are just created in our attempts to solve the problem. So in it, he goes on and talks about the value of having reliable primitive building blocks, which are pure functions. But yeah, I think Rich Hickey is great. To me, he kind of embodies the grumpy old developer that just wants to be happy and have a simpler life. And I've found that a lot of the Clojure community kind of embodies this as well. But I would recommend checking out his book, Joy of Clojure. It's like really inspiring, actually. Then there was this talk by Chad Fowler, From Homogeneous Monolith to Radically Heterogeneous Microservices Architecture. That's a hell of a title. But in it, there was a moment that really stood out to me. At this point, I had already kind of valued small functions. But in it, he talks about how he gives his developers one rule, that they can code in any language they want to, but whatever they build, it has to be this big. And he makes a big show about it. It has to be this big. And it got me thinking, like, wow, he's making a big deal about this. Like, is my small his small? And then I just... and then he goes on to talk about how the code should be disposable. If we're building things that are only this small, it doesn't take us any time to do it. So we can try out something fast, and if we don't like it, we can just throw it away. And this is a really great quality if we want to have like a flexible system design that can scale as our requirements change in ways that we never predicted. So yeah. That's great. And then finally, we have Sandy Metz, who I unofficially consider the queen of all things Ruby and object-oriented programming. And in her talk, All the Little Things, it's this beautiful refactor of the Gilded Rose Kata. You should check it out if you haven't seen it, but it's really incredible. And I don't know. I don't think it's like FP versus OP. One's not good, one's not bad. And like Sandy Metz is a clear example of how OOP can be amazing. But anyway, she starts out by explaining all the problems that we create have the same simple solution: to build smaller things and let them know as little as possible about each other. She also talks about how code has a natural tendency to go bigger, and that the reason for that is that when we're working on things, we kind of just implement it the way that we see it done already. Have you ever seen a 500+ long function that's like, it's a for loop, and inside of it is like a switch case, and inside of like all the cases is like multiple if-elses, which each have their own inner loops? I guarantee it didn't start that way. It started line by line over months and years. People saw, oh, this is the place that I make this decision, so I'll just add a little line here, which is not so bad when the function is only 10 lines big, but eventually it becomes 50 lines big, and you're like, oh, it doesn't matter if I add another 10 lines. And then it's like 1,000 lines long, and this is real life. And then we get to a point where we have no idea what this function actually does and what to expect out of it. And she also talks about it's far cheaper to keep duplication than the wrong abstraction, which is it's just a really great idea. I think as new programmers, we learn about dry, and it's something that's easy to understand. Don't repeat yourself. OK, I see a duplication. I make it into a function. But it turns out that it's way worse to create a bad abstraction. And if you immediately see duplication and abstract it away, it's probably too soon. You haven't seen the pattern in the code and seen the actual abstraction you want to create. So anyway, I want to add to dry. Don't instantly repeat yourself. So let that code sit a little bit before you decide to remove the duplication. And she also talks about open-close principle, which is a great quality for software to exhibit, which is that your code should be open for extension and closed for modification. That means that I can create new behaviors by adding code, and I don't have to change the existing code. That's pretty cool. Anyway, so thinking about all these influences, I've, over the years, slowly realized that functional programming actually naturally sort of makes these qualities just happen. They sort of fall into place pretty naturally. And I'll talk about why in a sec. I mentioned a bunch of organizational issues, and I want to be clear that functional programming is not a silver bullet, and it's not going to solve your organizational problems. For those, I would just want to give it a plug to Janelle Klein's idea flow. I think she has some really interesting ideas that are I want to see some organizations act on, but I'm not going to talk about that today. Anyway, idea flow, functional programming, just to kind of short and sweetly summarize what it is, it's kind of about preferring side effects, or preferring pure functions over side effects. It's preferring immutability over shared mutable state, preferring composition over inheritance, and preferring declarative over imperative programming. Again, this isn't good versus evil. This is just a functional approach. So in general, if I can, I'll do these things, but sometimes it's necessary and preferable to do these other things. Anyway, so it all started for me with JavaScript. JavaScript, it turns out, can be like anything to anyone, which can create some problems, but as far as functional programming goes, it has all the things that we need to functional program. It's got first-class functions and closures. First-class functions just means that I can pass a function around like data. I can assign it to a variable. I can create new functions on the fly. And that gives us the ability to do higher order functions, which is I have a function that either accepts a function and or returns a function. Eloquent JavaScript actually explains higher order functions really well. If you haven't read chapter 5, check it out. It's free online. But anyway, so yeah, functions as data, higher order functions. So higher order functions, a good example is like map, filter, reduce. They abstract away the for loop basically and apply some function inside of a loop. Let's take a look at what that looks like. So here we have for each, you've probably seen this a billion times. Log values just takes an array, and for each item in the array, I'm just going to log the value. And this is possible because somewhere on the array prototype, we have some function like this that takes a function as arguments and applies this signature to the function. So this is cool. This is a really easy way to kind of start understanding it. We can also do something like map. We can pass a function that pushes, that maps like the items in the original array to a new array. Same with filter. This is all possible with higher order functions. I take a function and do something with it. Reduce, I just wanted to show how this might be implemented. Reduce is one of my all-time favorite functions because it can do anything. Reduce can be used to like implement any of these other functions. It can do like crazy complex aggregations. You can use reduce to like create transducers, which is just like inside of the reduce function, I can have this complex like series of transformations that happen to each items instead of chaining like map, filter, and then a reduce. I could do it all at once for each item, which is great if you're working with like millions of items of data. Anyway, so this is first-class functions. Let's cover closures. JavaScript also has closures, and that just means it's a binding of the lexical scope to a function when the function is created. And I'll show you some examples of that in a second. Anyway, this is really important for functional programming because it enables partial application, and partial application leads to currying. We'll see why that's important in a second. But again, let's check out the code. So here we're creating a function, and we see that it returns this value. But this is actually in the outside scope. So when the function runs, it has knowledge of this thing that was there when it was defined. So every time I call this function, I'll have access to mdn.js URL. So that's a simple example of closure. But this is also apparent with our higher order functions. So when I call map, I get in this function, but I pass this function to for each, which has access to both the function that was passed into map and this value mapped that was defined outside of this function definition. So whenever this runs, I'm going to have access to this guy and this guy, even though neither of those were actually defined in this function. So that's closures. So closures give us the cool opportunity to do partial application, which is, let's say I have this low dashy kind of map. I take an array and an iterative, which is the function I want to be applied for the map. I can create a new kind of map, which takes the iterative first, and then the array, and then returns this. So I have a function that returns a function that accepts this and finally does your map. This is really powerful when we get deeper into functional programming. That means that I can define some sort of mapping operation independent of the data. So here I have, this is called like point-free notation. Just means I'm creating a function without explicitly listing the arguments that actually pass into it. So this is great, and you'll see this a lot in functional programming. It's more about thinking about the flow of data through the system and the transformations we want to apply to that data, instead of, I don't know, putting all the details into a function. That's just a good opportunity for what we talked about later. If you put everything there inside of the function, it grows bigger and bigger. But if we're able to do something like this and focus on little bitty transformations that we want to happen to our data, we can compose these functions in really interesting ways. Here's an example of how I might implement like a get. I take a key, which returns a function that accepts an object, which returns a function that, oh yeah, I wanted to do something more like this. That returns a function that every time I call it, I'll return that item from the source object. So that gives me the ability to do something like this with a user object. I can define a function that gets a name from any object. It's not tied to a user object. I can use this with anything that might have a name. And then I pass in a user, and now I have a function that always, it has closure over this user. So whenever I call this function, it will get me the name from that user. This isn't exactly the way we'd want to do it functionally, because we can see that with our set username, I'm going to be modifying this user every time. And later, we're going to get to immutability and why we don't necessarily want to do that. But anyway, this is cool because now I have these little functions that I've built up from smaller, simple, like little building blocks. Now I can do something like create a user that has some setters. Maybe I don't want to directly access an object. I want to provide some setters. Now I can get a list of users and easily create some setter functions on it. So I do this all the time, by the way. I love having a constructor function that really clearly defines the shape of some data that I'm working with. It means I don't have to go hunting down for what is the shape of this thing, which isn't necessarily a problem if you're working with TypeScript, and we'll get to that later. But anyway, so there's a lot of concepts there, and we'll expand on them later, but that's closures. So anyway, oh yeah, you get. Next, we have static types. Oh, but JavaScript doesn't have static types, but TS does. And static types come in real handy when we're doing functional programming because it's data-centric. I want to be able to know what the shape of the data that's moving through my system is, and I want to be able to verify that the data passing through my functions is sound. For example, with my users, if I am trying to access the name property of some random object, I want to know that the data that I pass through it has that property. And if it doesn't, I want something to yell at me when the code compiles and not when the users are filing bugs on the system. So anyway, yeah, it gives us that compile time verification. It's less mental computation because I don't have to compile the code in my head to figure out if it works. I can have the compiler and the IDE yell at me when things aren't right. It's a little bit more work, because you have to think a little bit more about, okay, I have to define this shape of object up front, but it pays off so much when you're debugging and or if you're refactoring, which is the next point. If I want to move some code around, I have some type system to yell at me if my signatures aren't matching up. And then finally, it's nice to have that kind of documentation in the code to tell me what the shape of everything is. I don't have, especially with intermediary objects, the objects that we create as we're transforming one thing to the thing that a function ultimately turns. It helps to not have to wonder, what the hell is this in the middle of this complex transformation? I can just see it in the code. And here's an example. So if I have this function prop_eq, which is a function that takes a string, it takes a value, an object, and returns a Boolean. I love this function. I use it all the time. But basically, it gives me the ability to create a function that accesses this key on some object. I pass it a value, and then when I finally get the object, I check that property to see if it's equal to the value I gave before. With TypeScript, I can compose a bunch of functions. Say I have this currency code eq, type eq, and I have this active price, which just says if the dates and a price are surrounding some original date, it gives me the ability to just look at the types here and just use my IDE to go and say, Oh, okay, I accept a list of price validators and I return a validator. That's super helpful. Anyway, so that's JavaScript. I also think we have a lot to owe to React for the rise in functional programming in JavaScript. Just want to read some blurbs from the docs. All React components must act like pure functions with respect to their props. And Redux is a big part of the React ecosystem. Immutability can bring increased performance to your app and leads to simpler programming and debugging, as data that never changes is easy to reason about than data that is free to be changed arbitrarily throughout your app, which makes a lot of sense when you think about it. If I have some data coming in and I decide to change something on it, maybe it seems harmless right now. No other functions are accessing data in this way. You don't know what's going to happen in the future when someone wants to use that object and it unexpectedly has values on it that change. This leads to unpredictable behavior. So immutability really helps us with keeping a consistent understanding of what's happening in our code. And then back to the React docs. This was actually interesting to read on the React docs. The key feature of React is composition of components. Components written by different people should work well together. It is important to us that you can add functionality to a component without causing rippling changes throughout the code base. And then finally, declarative views make your code more predictable and easier to debug. I've seen this list before. Aha! It's all of our functional programming principles. And it's no surprise then that the creator of React actually implemented first in a functional programming language called SML. It's a cousin to OCaml. And he's also creating ReasonML, which in the docs it calls it the language for writing React. I think this is a really promising, interesting project worth checking out if you want to do some pure functional code on the front end. So let's just dive a little bit more into some of these concepts. I have a lot of code I want to get to, and I'm really close to running out of time. So let's just breeze through this. Pure functions are referentially transparent. That just means that you can replace a function call with the value it returns without changing the meaning of the program. When I think about pure functions, I think about the words reliable. I trust it because it will always do the same thing. It'll always produce the same behavior. I call that function. 10 years from now, it's going to do the same thing. This is exactly the kind of building block that I want to build my programs on. Yeah, it's deterministic. It does the same thing every time. That means it doesn't modify shared state. It doesn't have side effects. And side effects are anything that modifies its input or causes some sort of side effect in the outside world, like IOs, your network calls. They're cacheable. And that's because, another way to say that is they're memoizable. Because they always return the same output through the same input, that means that I can remember the value that a function returned with the arguments. And when I call it with the same arguments again, I can just return that cache value. Parallelizable, easy to reason about, easy to test, easy to refactor. I don't have time to go into depth about all these, but I do want to show some pure functions. So pure function, the simplest pure function I can think of, an A that returns an A. This is anything I get, I return it. It doesn't do anything else. Add, I get some input, and I just return the sum. It's really easy to test. I don't have to worry about setting up a bunch of circumstances. I just think about the output that I would expect to get from the input. And here's some examples of an impurity. Here I have a function that's accessing some variable outside of it that could change. And here I have an increment that's modifying some state outside of it. This is examples of impurity, and obviously, if I'm doing a get, I have no certainty exactly what's going to happen, how long that request is going to take, all that kind of thing. Here's an example of a pure version of Git. This is actually, it may seem trivial, but this is really powerful as we get into the idea of having a predominantly functional, pure code base where we're pushing all of the impurities to the edge. This gives me the ability to create pure functions that, when called, are impure, but I can wait to execute this until I'm ready to put it in a place where at the end of my system where I want to actually have that happen. And then, of course, here's a React component. It's just a pure function. I get in some input, and I return this output. Let's see. Immutability is pretty straightforward, I think. You just don't modify anything after you create it, and that's because mutation is harder to reason about, as I explained earlier. And it may have unexpected consequences. Like I mentioned, I might think that it makes sense to mutate something right now, but that makes it harder in the future when I want to make changes. I have to worry about, oh, what else might be accessing this? All of a sudden, my focus is growing in scope beyond the function that I'm actually trying to work on. And immutability makes us happier and have a simple life. Let's talk about composition real quick. Composition is the bread and butter of functional programming. It's how we take a bunch of functions and compose them together into increasingly complex behavior. So this is valuable because it helps us to think about our code on a higher level. Instead of thinking about the low-level details, it gives us the ability to compose simple functions into increasingly complex behavior and express it in a language that represents our problem domain. And also, because it helps us eliminate some of the intermediate variables, it's literally when we're looking at a code, we have less variables that our brain is thinking about, which is good. The more that is happening in a function, the more your brain has to put in your head and wonder about what's happening here. I don't know. It drives me crazy working on big functions. But anyway, it reduces signal to noise because I'm capturing the essence of the transformations that I want to happen without getting into the nitty-gritty of how it happens. Yeah, and composition happens through partial application occurring. So here's some examples of composition happening in React. If you're not familiar with React, this is basically just pure function that returns what we're thinking of as the filter card, and I can take that element and then compose it into more things. So if I want a date filter, I can compose these range pickers. I can create a whole list of filters based on a bunch of components. This is possible. Oh man, I'm so out of time. I feel like I should wrap up with an example. I'm sorry guys, I didn't time this well. I just want to cover declarative programming real quick and show an example of it in practice. So declarative programming is basically it's doing what you want to happen instead of getting into details of how it should happen. So if someone tells you a recipe, they don't tell you Like, for example, like if I want to make a peanut butter and jelly sandwich, I just say, make a sandwich with peanut butter and jelly. I'm not going to tell you, like, go to the store, buy the jelly, buy the grape jelly, and buy the crunchy peanut butter. And then go home, get out a plate and put the bread on the plate, get a knife out of the drawer. I'm not going to like tell you every single step. I'm just going to like tell you like the high level of how it happens. And this is really important for programming because that leaves room for like me to do the same logic in different ways. I haven't hard-coded exactly how everything happens, so I can change the implementation details without any code depending on that worrying about it. So anyway, I just want to walk through a code example real quick. OK, so here, let's check this example out. Let's say I have a product. I've been working on pricing a lot lately, so all my examples, if you check out the code, are kind of pricing related. I want to get all the like prices from this project, from the product. The product has sizes, and the sizes also have prices, but the product also has some top-level default pricing. So in order to do this, I'm going to reduce the size pricing into a map so I can iterate over the top-level pricing, which has all the currencies that the product supports, so that I'm able to ensure that I have a price per currency if a size doesn't have it. And then I'm going to push this transformation of prices into the final array. So this might seem fine to some people, I don't know. But to me, there's so much happening in here. It's really a lot to take in. A more functional approach might be something like this, abstracting out how I get the size prices by I take a product, which takes a size, and then flat maps it. And we'll see how this all happens later. It maps each size to a price by taking in a product and the size. And then we'll get into how this happens later. Anyway, if you're not familiar with flat map, it's something like this. I just iterate over the items in an array, and you can think about flattening it. If each item is an array, I map it to something, and then basically get rid of the intermediary arrays. So I can represent get sizes with my simple prop function. Oh, I didn't get into combinators because I had to skip that section, but this is a really handy combinator. Combinators are like the glue of composition in functional programming. It's our way of combining functions in ways that maybe I didn't originally design the function for. Like, a function has one signature. I could either create a bunch of functions that have different signatures in like the ways that I want to use them in each case, or I can use combinators, which allow me to combine functions in ways that are helpful for composition. So anyway, pipe is like a really handy function. Just like you can think about passing in the arguments to the first function, which passes in the result of that as the arguments to the next function, so on and so forth. I don't have time to explain this, but man, I feel bad, but
Looking forward to the blog post, though.
Yeah, exactly. So I will do a blog post on this for you guys. I'm sorry this took so long, but check out the code. If you have questions, let's talk later, and then I can get into this with you. Anyway, thanks, guys.